In this video, we're going to go through the energy diagrams that we could possibly see for carboxylic acid derivatives. Looking at the first example, we're going to be looking at a downhill acyl substitution reaction with an anion nucleophile. So we're starting from our acid chloride and we're reacting with NaOCH2CH3, and that's preparing an ester. That means that we're going from a higher energy derivative to a lower energy derivative. Right away, that means we can cross off the far right two diagrams, because those are showing an uphill energetic transformation. We also know that we can cross off the very first diagram because that's showing that the starting structure and the ending structure are equal energy. And this mechanism specifically is only two steps. That will be this diagram here. Now, tracking the change with you, we know that in the very first step, the OCH2CH3 nucleophile would attack and break the pi bond, generating our tetrahedral structure. So we need to go up in energy to generate the tetrahedral intermediate. And from the tetrahedral intermediate, in this reaction, we would then collapse and kick out the chlorine leaving group. And the chlorine there is better at leaving than the OCH3. So we have a smaller energy of activation in the next step. We ultimately drop down in energy. Now consider this with me. If you're looking at the tetrahedral intermediate point on the diagram, from that point in the forward direction, we have a smaller energy of activation to kick out the chlorine ion. And if we were then to imagine the reverse, going from the tetrahedral intermediate back to the starting material, we would have had to kick out our poorer leaving group. And so the big takeaway that I want to have from this next few minutes of this video is this. From the tetrahedral intermediate, when you kick out the better leaving group, there will be a lower energy of activation in the direction where we kick out that better leaving group. But in the direction where we'd kick out the poorer leaving group from the tetrahedral intermediate, notice how there's a larger energy of activation for that to occur. In this case, we go up, forming the tetrahedral intermediate, then we collapse, kicking out the chlorine leaving group. Two-step diagram. Now, looking at the next reaction, this will be an uphill energetic acyl substitution. We're starting off with an ester, and we're reacting to form an anhydride, which is a higher energy derivative. So we're going uphill energetically. Now, this reaction, mind you, is not energetically favorable. Okay, it's not something that you can actually do. This is more of a what-if scenario. Now, the diagram that will correspond to this reaction is the far right diagram. Let's track the change together. The anion nucleophile, we'd imagine attacking right away. That would generate the tetrahedral structure. And in that tetrahedral structure, if we're actually going uphill energetically, we would have to collapse and kick out our alkoxide leaving group, which technically is the poorer leaving group in that tetrahedral structure. So zooming in on our diagram, we had to go up in energy to create the tetrahedral intermediate. And in the forward direction, we would be kicking out the poorer leaving group. If we imagine the reverse direction, just going back to the starting material, that has a lower energy of activation there from the tetrahedral because we would be kicking out the better leaving group. So a little bit funky here, we're going up in energy to form the tetrahedral. And then because we are kicking out the poorer of the two leaving groups in the tetrahedral, we have to go up even higher in energy in the next step. And ultimately, our product is higher in energy than our starting structure because we went from ester to anhydride. Now, what you'll notice is that this reaction here, this uphill acyl substitution, the diagram, is the exact reverse of the forward direction reaction of going downhill. In the very first diagram, we were starting at the acid chloride and we generated the ester, downhill acyl substitution. If you take this graph and you just kind of imagine flipping it over, that produces the graph here that corresponded to the uphill two-step acyl substitution reaction. And let's imagine this scenario where we start with one ester and we react with an alkoxide nucleophile and we generate another ester. We're going to think those esters are approximately isoenergetic, fairly similar in energy. And that means the energy diagram that would correspond to this reaction is the very first one. Let's consider that mechanistically, we would attack right away with our anion nucleophile. That would generate our tetrahedral structure here. And then in that tetrahedral structure, the two possible leaving groups are approximately the same. Okay. Now in the forward direction, we collapse and kick out the OCH2CH3 minus leaving group, but we could have just as easily collapsed and kicked out the OCH3 group because they're approximately equal in their leaving group propensity. Because of that, notice how the energy diagram here, we have similar energy at the beginning and at the end because we have two esters. And if we imagine the tetrahedral intermediate, you'll notice that the energy of activation here is approximately the same as the energy of activation here, because the two leaving groups that we could kick out from the tetrahedral are approximately the same in their leaving group propensity. Okay. Mind you, this reaction would be readily reversible. We could form that ester, and then this could add in and then kick out the OCH3 leaving group. Readily reversible reaction here. Isoenergetic acyl substitution. And finally, we could imagine a downhill acyl substitution reaction with a neutral nucleophile. Okay. One quick note here is that ET3N, that's going to be a non-nucleophilic base. It's very similar to pyridine. ET3N is just triethylamine, which functions very similarly to pyridine. If we're tracking the mechanism together, we're starting off with an acid chloride and we're reacting with an alcohol. That would attack the carbonyl carbon right away, breaking the pi bond. That would generate this tetrahedral structure here. And chlorine is definitively the best leaving group, so we would then collapse, kicking out the chlorine minus leaving group. That would then form an ester, but the oxygen here is carrying a positive charge still. In the next step, we would imagine ET3N, which I'll just write like this, acting as the base. That would deprotonate the oxygen atom, forming your ester product. So here there's a total of 3 steps, downhill acyl substitution reaction. Tracking the change in the diagram. We started off at our ester. We reacted to form the tetrahedral intermediate. That would be the rate determining step. And then we kicked out the better leaving group, the Cl- ions, from that tetrahedral structure. In the forward direction, we have the smaller energy of activation in that step to kick out the better leaving group. That then formed a charged intermediate, and then ET3N deprotonated. 3-step energy diagram. Attack, eliminate the leaving group, and then deprotonate. The other energy diagrams were only 2 steps because we were reacting with an anion nucleophile. And after we attacked with the anion nucleophile, we eliminated to form our final product. And there was no deprotonation required. So we have a downhill acyl substitution reaction with an anion nucleophile, 2 steps. We go up in energy. And then in the second step, we had a lower energy of activation barrier and kick out the better leaving group. If we're doing an uphill energetic acyl substitution reaction, we need to go uphill energetically to begin with to create the tetrahedral. And then as we're kicking out the poorer leaving group, we need to go even higher in the second step. And ultimately, we're ending up with a higher energy derivative, which, remember, this is not actually a reaction that you can do, say, in synthesis. This is more of a what-if scenario to consider the energy diagram. We then looked at an isoenergetic acyl substitution, going from one ester to another ester. In the diagram, the start and end was the same, because esters are approximately equal in energy, and from the tetrahedral intermediate, the energy of activation in the reverse direction and the forward direction is approximately the same, because the leaving groups in the tetrahedral structure were approximately equal in their leaving group propensity. And finally, we looked at a downhill acyl substitution reaction involving a neutral nucleophile. That was a 3-step mechanism. We went up in energy to begin with, forming the tetrahedral. We then hit a lower energy barrier as we kick out the better leaving group. And then we had to have a deprotonation step where ET3N functions as the base, deprotonating to form our ester.